All right, let's get started on the first video lecture for our Unit 7, which is on gases. And I'm going to start by actually talking about something that's going to seem unrelated to gases, but will come back into play later, called intermolecular forces, or IMFs. So as a review, we talked about Coulombic attraction way back in the day when we talked about bonding. Just a review of that, Coulombic attraction is the fancy term for opposite charges attract and like charges repel. So when I talk about Coulombic attraction, hopefully you remember opposite charges attract. So what the heck is an intermolecular force? It is a force found between particles. So it can be between atoms, it can be between molecules, and it's what holds those particles together. It is not a bond. There are 6 different types of IMFs. However, we will only cover 3 in this class. I cover the other 3 in AP Chem. So like I just said, IMFs are not bonds. They're not the same thing. Bonds are called intramolecular forces because they exist within a molecule. So like this bond between the H and the Cl in hydrochloric acid, that's an intramolecular force. IMFs are intermolecular forces because they exist between molecules. So it holds these hydrochloric acid molecules together. It is not an actual bond. Okay? So ionic bonds, covalent bonds, metallic bonds, those are not IMFs. The first of the 3 IMFs that we're going to talk about, I'm going to go weakest to strongest here, are called London dispersion forces, or LDFs. An LDF is a very temporary attractive force that results from the random movement of electrons within an atom or within a particle. So if this is an atom, there's a bunch of electrons that we know occupy these orbitals, which are just regions of space that the electrons are free to move around in. So statistically, there is always going to be a chance that electrons are going to randomly be unevenly distributed throughout a particle, meaning there's going to be times where there's going to be more electrons on one side of an atom or one side of a molecule than the other. And when you have more negatively charged electrons on one side versus the other, you form these partial charges. So the side that has the more electrons will have a slightly negative charge, and the other side that has less electrons will have a slightly positive charge. And this just randomly happens. When a particle, right, an atom or a molecule, forms those partial charges because of the uneven distribution of electrons, it can cause neighboring particles to also form partial charges. So for instance, if this is my particle that just randomly has all these electrons over on the right, giving that side a partially negative charge and giving the other side a partial positive charge, and it comes into contact with another molecule, or particle I should say, that doesn't have that, what's going to happen is this partial negative portion of the molecule whose electrons are unevenly distributed is going to repel the electrons in a neighboring particle, pushing them to the other side, giving that particle a partial positive charge and negative charge due to the uneven distribution of electrons in the first particle. So the random distribution of these electrons causes electrons to be unevenly distributed in neighboring particles. which is going to form partial charges in the neighboring particles, which we know then opposites attract. So the attraction between these slight charges would be called an LDF. Now, what's important to note about LDFs is these are going to exist between all molecules and atoms. Any particle can form LDFs because every particle has electrons that are randomly moving and can just naturally be unevenly distributed. This is the only type of IMF that will be present in nonpolar molecules. Only one. But this is found in every single particle, doesn't matter what it is. They're very short-lived because the electrons move randomly. That's why they form the LDFs in the first place. So the electrons will just naturally move back to being evenly distributed very quickly. And this is the weakest of the three IMFs that I'm going to talk about. Now there's two things that we can look at to determine the strength of the LDFs that are found within a substance. The first one we can look at is the number of electrons. So the more electrons that a particle has, the stronger the LDFs will be when they form them. The reason is because when you have more electrons, when you have more of them on one side of a particle versus another, your partial charge is going to be a little bit stronger just because you have more negative charges in that region. So like lithium only having 3 electrons, if 2 of the 3 are on the left and 1 is on the right, you'll have a slightly negative charge over here on the left, but it won't be nearly as strong of a charge as if we look at potassium, who has 19 electrons, if they have, let's say, 15 electrons over on the left and 4 on the right. So the more electrons you can have on one side versus another is going to increase the strength of the partial charges, which will increase the strength of the LDF that forms between neighboring particles. The second thing we can look at is the size of the molecule. So the strength of the LDF increases when you increase the size of the molecule, which goes back to the first bullet that says, like, the bigger the molecule, the more electrons there are, which means that we're going to have stronger LDFs. So looking at these two molecules, this is methane, this is butane. Butane would be able to form stronger LDFs than methane because it's bigger, so therefore it contains more electrons. And when those electrons are unevenly distributed, it'll form stronger partial charges than the methane. So that is it for LDFs. Let's review something real quick before we get into the second type of IMF, and that is a dipole. A dipole is looking at a molecule that contains permanent regions of partial charge, which we've been calling these polar molecules. So polar molecules contain permanent dipoles, which is why they contain permanent partial charges. So like water contains a dipole because the oxygen has always a partially negative charge and the hydrogens are partially positive. So if you're able to look at a molecule and determine if it's polar or not, then you can determine whether it has this second type of IMF that I'm going to get to in a second. So remember, ways to identify a polar molecule. First, has non-bonding electrons on your central atom. Like water is an example. We have non-bonding electrons on the oxygen, automatically polar. Second, if there is a mixture of types of bonds. So you have both polar and nonpolar bonds within a molecule. That makes the molecule polar. It will contain a dipole. And also, if you just have two atoms bonded together and that bond is polar, the molecule will be polar. So if you have a polar molecule, it can form dipole-dipole interactions, which are the second type of IMF. So dipole-dipole interaction is the Coulombic attraction that forms between polar molecules that contain permanent partial charges. So the difference between an LDF and a dipole-dipole is LDFs form because of temporary partial charges. Dipole-dipole interactions form because of permanent partial charges. So all polar molecules, doesn't matter how polar, as long as they are polar, will be able to form dipole-dipole interactions with itself. Like we see here, we have ICl, which is a polar molecule. It can form dipole-dipole interactions, which I've highlighted in blue, with itself. But if I also were to throw in another polar molecule like water, it could also form dipole-dipole interactions with the water. The third type of IMF is hydrogen bonding, which we have talked about before. You've learned about it in biology. We've talked about it here in chem. This is actually not a bond, even though it's called hydrogen bonding. It is actually just an intermolecular force. So what a hydrogen bond is the Coulombic attraction found between molecules containing a fluorine hydrogen, oxygen hydrogen, or nitrogen hydrogen bond. So if you see any of these bonds, when you draw out a Lewis diagram or you look at a formula, if you see these bonds, that molecule, any one of those bonds, that doesn't have to be all three, that molecule is able to form hydrogen bonds with itself, or with another molecule that can also form hydrogen bonds. This is the strongest of the three IMFs, and the reason being is because hydrogen only has one electron. So when it bonds to a really highly electronegative atom like fluorine, oxygen, or nitrogen, that electron gets pulled to one side of the nucleus, leaving nothing on the other side of the hydrogen, which means that the partial positive charge that forms there is just a little bit stronger than what it would be in a regular polar molecule. So for instance, like this partial positive here is not as strong because the iodine has electrons on this side of the atom, whereas with something like water, the one electron that hydrogen has is going into this bond, so there's nothing over here. So this slightly partial, or the partial positive charge that forms here is going to be stronger because there's no negatively charged electrons there, versus here there are some, so it lowers the positive charge. So let's do some examples. With IMFs, you do need to be able to recognize what kinds of IMFs a substance can form with itself. Also, I'd be able to figure out what kind of IMFs a substance can form with another substance. But let's start here. For each of the substances, we want to know what IMFs can the molecules form with themselves. So starting with A, C2H6, it sometimes helps if you can't visualize the bonds within a molecule to draw the Lewis diagram first. So C2H6 is two carbons bonded together, and each carbon has three hydrogens attached to it. All of the bonds in that molecule are nonpolar. There are no non-bonding electrons on the carbons at all, which makes C2H6 nonpolar. Whenever you have a nonpolar molecule, the only IMF that it can form are LDFs. That's the only thing it can form. There's no dipole. It's not polar. I do not have an oxygen-hydrogen, fluorine-hydrogen, nitrogen-hydrogen bond. So it's just LDFs. For B, for pH3, if you were to draw that out Lewis diagram form, you have a phosphorus in the middle with 3 hydrogens coming off of it, and the phosphorus has a pair of non-bonding electrons on the top of it. So all molecules automatically form LDFs. So that's one option for pH3. But because pH3 has that non-bonding pair of electrons on the phosphorus, that gives it a dipole, which means that it can form dipole-dipole interactions as well. It's a polar molecule. However, it cannot form hydrogen bonds because it does not contain a fluorine-hydrogen, oxygen-hydrogen, or nitrogen-hydrogen bond. It's all phosphorus-hydrogen, which is not one of them. So therefore, it can only form LDFs and dipole-dipole. For H2O, automatically can form LDFs. We talked about water having a dipole, meaning it's a polar molecule, so it can form dipole-dipole interactions. But it also contains an oxygen-hydrogen bond, actually 2 of them, so that means that it can form all 3 types of IMFs. I want you to pause the video here, see if you can determine the types of IMFs that each of these particles can form, and then hit play when you're ready. So HF is just a hydrogen bonded to a fluorine. Automatically can form LDFs because every particle can form LDFs. It is polar, so therefore it can form dipole-dipole interactions. And it contains a fluorine-hydrogen bond, so you should have said that HF can form LDFs, dipole-dipole, and hydrogen bonding. For CO2, automatically can form LDFs. CO2 is nonpolar. It has 2 polar bonds with symmetry, so they cancel out, making the molecule nonpolar, which means it cannot form dipole-dipole interactions, and it doesn't contain a fluorine-hydrogen, oxygen-hydrogen, or nitrogen-hydrogen bond, so CO2 can only form LDFs. For HCl, it's a hydrogen just bonded to a chlorine, can form LDFs. It is polar in nature, so it can form dipole-dipole interactions, but it does not contain one of the 3 bonds that allows it to form hydrogen bonding, so it would just be LDFs and dipole-dipole. So if I put the strength of the IMFs in order from weakest to strongest, LDFs is the weakest, dipole-dipole is the second middle strongest, and hydrogen bonding is the strongest. A couple things for application of IMFs. First off, boiling and melting points. Let's talk about what they are first, and then I'll get into the application. So boiling point is the temperature at which a substance changes from a liquid to a gas, aka when it boils. The melting point is the temperature at which a substance changes from solid to liquid, aka when it melts. When you change the state of matter, bonds between the atoms are not broken. Only IMFs are broken. So when we look at how boiling and melting points differ from substance to substance, it's based on the strength of their IMFs. So the stronger the IMFs, the higher the boiling and melting points are going to be, because it requires more energy to change states, because we have to break stronger IMFs, which requires more energy. Viscosity is also something that's affected by IMFs. So viscosity is the resistance to flow. It's how thick a substance is. Usually we're talking about liquids here. So the higher viscosity, the harder it is to pour, the harder it is to stir. So when a substance has stronger IMFs, it's going to have a higher viscosity. It's going to be thicker because there's stronger attractive forces between the particles, making it less likely to flow or making it harder to stir. So for our next example problem, we want to know which substance would have the highest boiling point and then explain why. So we have CCl4 and we have CHCl3. First thing to look at is the types of IMFs that are present in each particle. CCl4, if you draw the Lewis diagram, has a carbon in the middle, 4 chlorines coming off. Each of the carbon-chlorine bonds is polar. However, hopefully you remember tetrahedral molecules have symmetry, which means all those polar bonds cancel out, making CCl4 non-polar. That means that the only IMFs that CCl4 can form are LDFs. For CHCl3, it's the same Lewis diagram, but one of the chlorines is substituted with the hydrogen, which means there's both polar and non-polar bonds present, because carbon-hydrogen is non-polar. Because there's a mixture of types of bonds, that makes CHCl3 polar, which means it can form LDFs and dipole-dipole interactions. So, because the CHCl3 has the ability to form stronger IMFs, LDFs and dipole-dipole, it would have the higher boiling point. So the way to determine which substance has a higher boiling point or which substance has a higher viscosity is to compare types of IMFs. Why don't you pause the video, see if you can get this question on your own, and then hit play when you're ready. So to determine which substance would have the lower viscosity, we are looking for which substance has the weaker IMFs. Both of these molecules would contain only carbons and hydrogens, which means that they're both nonpolar. So they both can only form LDFs. However, one of them is smaller than the other. And we know that the smaller the molecule, the weaker the LDFs will be. The weaker the LDFs, the lower the viscosity. So the C3H8, because it's smaller, it contains fewer electrons, its LDFs will be weaker, giving it a lower viscosity. And that is going to be it for this video lecture.